So good morning again. I will do now the same method as before this morning, but for perforated domain, explaining also the specificity of perforated domains. Now, okay, I am conscious that this morning was a little bit fast for many of you students, but my idea is that those who are more advanced can follow all the details, although quickly. The other one, just keep the ideas, then you have to study the notes because I cannot do too slower. Otherwise, normally I can do that in a 20-hour course, so okay. Okay, so perforated domain. Okay, you have a long program. Maybe I will go on the next time. I will not do everything today. Let us start with the motivation. So we have oscillation in the coefficient in the model case, but we have also oscillation which can come from the domains. As Edith C, look, for instance, here you have a lot of small holes, which are periodic. Actually, this looks like probably double periodic structure. So you can have perforated domain, you can have a reticulated structure, oscillating boundary. For instance, some pictures for holes, you can have sponge, you can have this kind of material, you have shoes who allow you to transpire because they have a lot of small holes and the water do not enter inside, so you have to choose conveniently the size of the holes. Okay, now you can have also this kind of structure which are also periodic, always with this idea that what is important is the number of things who are repeated compared with the global size, so it can be very small or very big, it depends. Another truss, and oscillating boundary can be like that, you know, like the wheels, shoes again. Okay, anyhow, my colleagues will talk in details about oscillating boundaries. So I come back to the periodically perforated domain. This is the same picture as before, but what is the difference? The difference is now yellow part is not anymore a second material, but is simply empty. So we have holes. Let us observe also that holes can also be not physically holes, but can be non-conducting material. For instance, you have an electric problem, you have isolated balls, for instance, inside, and it's like also the equation do not see the difference between no material and material who do not follow the equation. So it's in some sense the same. Okay, but let us talk about perforation. So we do the same change of scale than before, and we have the reference cell again. This time, okay, we are interested in this set, which is y star equal y minus t. Okay, probably the hole sometimes will be called t, sometimes s, I am realizing now, so I am sorry for that, but for the moment it's t. Okay, so our reference situation now is this is y, this is our t, and so this part is y star. Then we do the change of scale. So we take all the reference, all the holes as before. Okay, but I will avoid picture. And we consider all the holes included which intersect omega. And here we assume that the holes do not intersect the boundary of the holes. So, okay, this is not so nice assumption, because that means that in practice epsilon should be some power of 2, for instance, or and the domain has to be union of period. Okay, mathematically it doesn't matter, but even is a not nice assumption, but this is the historical assumption. It's needed really in this context only for Neumann, not for the Dirichlet condition. But now with unfolding this hypothesis, or to scale this hypothesis is not anymore necessary. Okay, now we define omega epsilon, omega minus the set of the holes. In this context, the boundaries are well separated actually. Okay, and here the holes have the same size at the period. At the end of this talk, or maybe next talk, I will say a few words about the situation where the holes are of a smaller size than the period, which mathematically is completely different situation. Okay, now let us define key omega, the characteristic function of a set omega. That means key omega is the function. This is equal to 1 if x belongs to omega and 0 outside. Okay? And then we also define m omega, the average. This morning, Ravi discussed a lot about average. We denote by v tilde the zero extension to Rn of any function defined on omega or t. And let us look, so the characteristic function of our perforated domain. Since the domain is obtained by the change of scale, also the characteristic function is obtained by change of scale, so is the form key y star of x over epsilon. So, usual rule, it converges to the average of key y star. What is the average of key y star? The average on y of key y star is 1 over y, integral over y of key y star of y dy. Okay, but what is key y star of y? But is 1 on y star, is 0 outside. So actually, this is 1 over y, integral of y star of 1 dy. This is the measure of y star, so it's exactly the measure of y star over y. Okay? This is a key quantity in the study, so let us keep in mind, we denote here by theta, and this is the proportion between the volume of the non-perforated cell with the full cell. So actually theta represents the proportion of material. Okay. What happens? Yeah, I will plug, otherwise it will be stopped all the time. Okay, so so what we have to emphasize is that if the hole is not empty, which is not an interesting case, then about y star is not equal to y. That means that theta is lower than 1 strictly, and obviously theta is not 0 because y star has some measure. Okay. So this convergence is weak and is not strong as we know. Okay. Now consider our problem. Our problem is as before. Okay, you remember that I have just observed that we have actually our domain like that, more or less. Here we have the holes. Here we have the exterior boundary, the omega. Okay, so the idea is consider the usual problem minus divergence epsilon gradient to epsilon equal f in omega epsilon. Put Dirichlet condition on the exterior boundary. This is not so important physically, but it's very useful in maths because it avoids some technical question. And we put some boundary condition on those. F for simplicity in L2, A epsilon as before, defined everywhere, epsilon periodic in M alpha beta Y. Okay, so what is the first difficulty we'll meet? Is that, okay, we want to study the convergence of the solution. But what means the convergence of solution? If the solution, any solution is on space. So how we can talk about convergence? Then we have to find a solution for that problem because we need the common space. Okay. In some cases, easy for some boundary condition. For some boundary condition, it will be difficult. I will explain why. Okay, I wrote A epsilon, but if you take the Laplacian, the difficulty are exactly the same. So you don't pay more putting A epsilon if you want to think to the Laplacian. This is a difference with the previous case. In the previous case, if you take the Laplacian, you have no oscillation anymore, you have nothing to do. But here, even if you use, you take A epsilon equal the identity, you have all the same difficulties. Okay? We put the Dirichlet condition on the exterior boundary in order to have a Poincare inequality, which is always useful. And the boundary condition take an essential role. Hence, different boundary condition give rise to a different homogenized problem, a different situation. Okay, let us see what kind of boundary condition we want to study. We denote n the outward unit normal to the domain. Then we consider the following condition: homogeneous Dirichlet condition, homogeneous Neumann condition, non-homogeneous Neumann condition, non-homogeneous Robin condition. Okay, actually I will talk about the first two, then the fourth one, this one being a particular case of that one. Okay. But this one, even if it's a particular case of this one, is better to do alone in the beginning because otherwise it's too complicated to study directly Robin condition. Okay, so yeah, I refer to the book of Cioranescu and Jean Paulin where all that things are well studied. Okay, then let us start with the homogeneous Dirichlet boundary condition, which is not so often discussed because it's not considered so interesting, but in some sense it's important to show here what this case, because it's the natural idea. We have done Dirichlet in the previous case, we put those, we study Dirichlet, we see what happens. Then we decide if to study other cases. So we put Dirichlet condition everywhere. We know because we have studied already that we have a unique solution, which is there. And also, we have proved, I stated this morning a result on the function in H10, which say that if you make an extension by 0, you remain in the space and the norm are the same. So, we can extend the functions to the whole of omega. And we have that alpha u epsilon tilde square in H10 is equal to the same norm, the norm of u epsilon in the space with the omega epsilon. Here, by ellipticity of A, you have this inequality. This is the equation. Here you do Elder and you estimate the norm of u epsilon by that u epsilon tilde because it's bigger. And then you can use, once we are in omega, we can use the Poincare constant in omega. And then this one is exactly, okay, so we have this one. So this one and this one cancel and we get an estimate on u tilde epsilon. Okay, everybody follow? Okay, consequently, the norm of U tilde epsilon in H10 of omega is bounded with the constant which is independent on U epsilon. Okay, now we can use compactness. Compactness because we have an estimate in the bool. Now all the functions are in the same functional space. So we are fine because we can discuss as before compactness, convergence, and so on. So we have that U tilde epsilon converges to U in H10 of omega, and the zero extension converges to U strongly in L2 of omega. Then we have, this problem was studied for the first time by Ceaurescu and Champolin in 78, as far as I remember, as well as the Neumann case. And then, okay, the result is that actually U is zero. Is quite surprising. That means that actually the zero extension goes to zero weakly in H10 and strongly, anzi, even more, the convergence in H10 is a strong convergence to zero. Okay, what does it mean? That means that actually, in some sense, the zone occupied by the holes, where the function is zero, is so big that at the limit is that, okay, it's zero everywhere. This is more or less the intuitive idea. The proof of that proposition, okay, consider now key T epsilon, which is the characteristic function of the holes, which is nothing else than one minus the other one. Because it's a complementary set. So, if we consider the product U epsilon tilde key T epsilon, then U epsilon tilde is zero on the holes. Key T epsilon is zero outside of the holes, so the product is zero everywhere. Then we can, now we know that this one goes strongly to U, capital U. This one goes strongly to 1 minus theta because it is nothing else than 1 minus that function. So we have U 1 minus theta equals 0. But theta is not 1, so U is equal 0. This shows the first part of the proof. Okay? Question? We pass to the limit here. This is a strong weak limit, so we know that it converges to the product, which is this one go to U, this one go to 1 minus theta, so it's done. Sorry? Yeah. Then, on the other hand, if we look at the norm of U tilde epsilon in H10 is equal to the integral over omega epsilon F U epsilon, which is exactly the integral over omega F U tilde epsilon, but this one goes to 0, so this goes to 0, so the norm in H10 goes to 0. That means that you have a convergence, stronger convergence to 0. Okay. Yes, this is nice, although we expected maybe more to understand more this problem. Okay, actually this is very rough. We can do better. It was done by Lyons originally. So, first one observed that in omega epsilon one can prove a Poincare inequality. Before we used through the extension operator, we used the constant of omega. But actually we can have this estimate where the constant is C times epsilon in omega 1, 0 omega epsilon. Why that? Because, okay, I don't want to enter in details, but actually when you prove Poincare inequality in a ball, for instance, what you do? You are somewhere, you try to reach the boundary, and you make the difference between the function here, and then you use the theorem of the calculus and so on, and use the fact that you are here, here is 0, and you consider this distance. So what is important is the distance of any point to some point of the boundary where you have 0. Now, here, in the perforated domain, actually, you take any point, but you are not far more than epsilon to a hole where, so to the boundary of a hole where you put 0. So the constant is of order epsilon. Okay, this is roughly speaking, you can even, okay, anyhow you can do the proof and you see that it's like that. And even this is true in more general situation, but okay. Okay, so this was the Poincaré inequality. So if you look at that, you start to understand that there is some looping, some bootstrap in the sense that, okay, this one was bounded, now you put epsilon, so this one was bounded, but now it's more than bounded, it's of order epsilon. So we have the following results from Lyons, Tartar, also Tartar did something for the Stokes cases. Okay, so actually, U epsilon tilde is of order epsilon in H10 and of order minus epsilon square in L2. So what happens is that epsilon U tilde epsilon goes weakly to 0 in H10 of omega. Epsilon square U tilde epsilon weakly converges to FW0, where W0 is the average on Y of this problem, which looks very far for the problem originally, I mean, which is minus divergence of the transposed of A gradient W equal 1, W equals 0, oops, W equals 0 on the T and WY periodic. Okay, so here, there are no limit equations, but the limits above are explicit because you compute one is 0, the other one is FW0, so you don't need, in general, you look for a limit equation because you don't know what is the limit. But if you have the limit, anyhow, you have finished. Okay, so the proof is not so difficult if you know a little bit of functional analysis, because, okay, we start as before. So we have alpha U epsilon square H10 of omega epsilon. This is equal to the integral of F U epsilon. You estimate this one with the U epsilon in L2, F in L2. Here we don't pass to the 0 extension, because if we pass to the 0 extension, we cannot use Poincaré in omega epsilon. So for the moment, we stay in the perforated domain for the estimate. Then we can estimate this one by constant epsilon, the norm of U epsilon times F. Then, simplifying this one with the square, we get that the sequence U epsilon is smaller than epsilon times F, so that epsilon minus 1 norm U epsilon in H10 of omega epsilon is bounded. And now we use again Poincaré, because you have seen if, okay, so if we prove now that the gradient of U is not constant, but is better, is of order 1 over, you can estimate of order epsilon, then you have epsilon, epsilon, that means that U is order epsilon square. Then, so in conclusion, epsilon minus 1 U epsilon is bounded, epsilon minus 2 U epsilon is bounded. Then, extending by 0, we have the same estimates. By compactness, we have that there exists U star and U0, such that epsilon minus 1 U tilde epsilon converges weakly to U star, and strongly in L2, and epsilon minus 2 u tilde epsilon converges weakly to u0. Okay, now, okay, observe that epsilon minus 1 u tilde is nothing else than epsilon times epsilon minus 2 u tilde epsilon. So this converges, this is bounded in L2, multiplied by that 1, goes to 0. So we deduce that u star, I don't know if it's correct. We have that this one is bounded there. Maybe it's the contrary, actually. We have to use, no, yeah, okay. Yes, so we have the strong convergence, sorry, of this one, because this is weak, but we have strong convergence in L2, so this one goes to 0, so u star is 0. Okay. Now, we want to identify the limit of epsilon minus 2 u epsilon tilde. And then we use again more or less the Tartar method. Actually, as far as I know, maybe Tartar did first this problem for Stokes, and then the method was working for a lot of other cases. So we have W, that function W, we periodize by this relation, and we extended, where we extended by 0 to the full T. Okay, then epsilon, W epsilon is bounded in H10, W epsilon is bounded in L2, so that epsilon, W epsilon goes to 0, and the W epsilon converges weakly to W0 in L2. Okay, here we are interested to look at epsilon, W epsilon instead of putting here epsilon. Okay, so now by change of scale as before, we have this equation in the rule of omega epsilon. Here we have epsilon to the power minus 2, because before it was 1, but then you have two derivatives, one from the gradient, the other one from the divergence, then you get 2 epsilon, in twice epsilon, in which we can put here. Okay, so we have the equation W, no, not really, we have a gradient here, gradient W epsilon, gradient V equal epsilon minus 2 V dx. Okay, now the Tartar the machine works, so we take phi in D of omega, we choose a phi W epsilon as test function in the problem of U epsilon, phi U epsilon, the equation solved by W epsilon. We have all those terms. We cancel the pink term as before, and that's fine. And in the other one, we are able to pass to the limit. Why? Because now what happens is that this term, I don't know if I put the details in the following, no, not yet. No, so okay, here we have that W epsilon is bounded, A epsilon gradient U epsilon is of order epsilon, the other one is of order epsilon, this is bounded, in conclusion those terms goes to 0. So the right-hand side goes to 0. Then we have 0 equal the limit of the right-hand side, and now here we can extend by 0, W epsilon is defined in omega, Phi, here we extend U epsilon by 0. We have the right coefficient, epsilon minus 2, because epsilon minus 2 U tilde epsilon is weak converging to something which is not a priori 0. So this one converges to phi u tilde 0, this one to f phi w0. That means that we have this equality for every phi in d of omega. Okay, now as we observed when we discussed the scalar product, which is here, if this is 0 for every test function in D, that means that actually they are equal everywhere. And so U0 is equal to FW0, almost everywhere. And then we finish the proof. Okay. Okay, so this case is concluded. We have nothing to add. We know the limits and everything for the moment. Now, let us look the case of homogeneous Neumann boundary condition, which is a completely different situation. I have not discussed this problem in my previous talk because it was too long, but I will say a few things here because we consider the problem. So we leave the Dirichlet condition in the exterior boundary. So here we put Dirichlet, and on the boundary of all the holes we put Neumann, homogeneous Neumann condition, and we define the space of the function which are in here also there is a misprint, this V in H1 of omega epsilon and 0 on the omega, in the sense of the trace. So the zero, observe now, okay, so I will write the space V because there is a misprint. V is equal to the space of V in H1 of omega epsilon, such that V equals 0 on the omega. Okay, so so now we have a difficulty because we cannot just, as before, extend merely by 0 the function. We can, but the function will be only in L2, they will be not in H1 because it will have a jump on the boundary of the holes, because on the boundary of the holes originally the function of V epsilon, they are not 0. So from the exterior, if you extend the function by 0, from outside the trace here will be 0, from inside the trace will be something else, and the function in H1 have a trace which is the same from both sides of a line, let us say. So we need some suitable extension operator, which make also all the difference with unfolding, because as we will see, then unfolding will not need extension operator. Okay, so let us call extension operator. We suppose that the boundary dt of the reference hole is Lipschitz continuous. And then we have the following results, which is due to Doinac-Ranescu and Janice and Jean-Paulin, who did the following things. So one can find an extension operator that means such that is continuous from H1 y star to H1, continuous from L2 of y star to L2 of y, such that the norm of the extension in L2 is smaller or equal than the norm, constant norm, the V in L2 of omega star. And the gradient of the extension in L2 is lower or equal than the gradient of V in L2 the y star. Okay. What is the novelty of this extension operator? Because extension operators are known in the literature for Sobolev spaces, is that in general, what you have in general, you have that there exists an extension operator such that function u in H1 of, let us say, even omega epsilon, associate pu, which belongs to H1 of omega, and you have that the norm of PU of in H1 of omega is smaller or equal than the norm of PU of U in H1 of omega star, of omega epsilon. Okay, so this is the general results that, and you cannot separate here the norm of the function and the norm of the gradient. In particular, the norm of the gradient is estimated by the total norm here. But the feature here is that you can, the idea here is using a suitable inequality which is called the Wirtinger-Poincaré inequality. You can show that you, sorry. You can show that you can estimate the gradient in L2 by the gradient the gradient of the extension by the gradient of V in L2 of Y star. And this one is not the norm in H1, it's a part of the norm in H1 because there is not the norm of the function. Okay. Then one can make a change of scale. And by change of scale, summing, okay, one obtain that actually one have the same results from omega epsilon to H10. That means that you can find a linear continuous extension operator, which is linear continuous from L2 of omega epsilon in L2 of omega. No, here also there is a mistake. This is L2 omega epsilon, L2 omega. Intersection V epsilon H10, such that you estimate the norm of in L2 by the norm L2 and the norm L2 of the gradient by the norm of L2, the function. Then, thanks to this result, one can prove a Poincaré inequality in omega epsilon, which is independent on epsilon. We already, indeed, one do the following things. But now is Poincaré inequality in V epsilon, not in H10. And how one do, you say that the norm of V in L2 is smaller than the norm of the extension. Then here you use here you use the estimate, the Poincaré inequality in omega. Sorry, C omega is badly, it should be outside. In L2, and this is smaller or equal than C omega, gradient of V1 in L2 thanks to the extension operator. As a consequence, the norm of V in L2 epsilon is smaller or equal than constant norm of V in L2. I don't know, this one has nothing to do, sorry. And then as corollary, this quantity is a norm equivalent to the H1 norm, the norm of the gradient. So this gives to the function a behavior which looks more like H10, although we have not prescribed the Dirichlet condition on the boundary. Okay, now we define the variational formulation of this problem. One can show that the variational formulation is the following. Find U epsilon in V epsilon such that A epsilon gradient V is equal to the integral of that for every V belonging to V epsilon. What is the difference of this variational formulation with respect to that for Dirichlet? The integral here, this equality is the same. So there is a difference or not? Sorry? Which domain? I know. The other one, the space. That means that before we put here, find the u in h10 of omega epsilon, such that, tac, tac, for every v in the same space h10. But here, we require that for functions in v epsilon, which are not zero on those. So, although the variational formulation looks the same, the problem is not at all the same. Because the tests are in different space, and we look the solution in the different space. So, okay, but now thanks we can thanks to the uniform Poincare inequality, we can still apply the Lax-Milgram theorem to prove that for every epsilon we have a unique solution, u epsilon in v epsilon. Moreover, we have the following a priori estimates. We can estimate the norm of u epsilon in v epsilon by a constant c, which do not depend on epsilon, divided by alpha, multiplied by the norm of f in L2 of omega epsilon. Okay, now this one can be estimated by the norm in L2 without epsilon, in L2 complete. And this one is bigger than constant times the norm in H10. In conclusion, using the extension operator, we deduce that we have that this one, which is smaller than the norm of u epsilon in omega epsilon, is smaller than this quality. Here, epsilon should be removed, okay? Then there exists u0 in H10 such that up to a subsequence, as before, p epsilon, u epsilon weakly converges to u0 and strongly in L2. Okay, so we have now all the convergences as before, and okay. As I saw before, clearly we could consider the zero extension, but we have no gain instead because the function will be only in L2 and not in H1. Okay, so there exists a function u in L2 such that up to a subsequence, the zero extension u epsilon converges weakly to u in L2 also. And we want to compare the u0 and the u. The limit of, because we know that there are zero extension in L2, we know that there are extension operator in H10, and we want to know is u0 equal to u or what? And what we obtain is that actually capital U is theta u0. That means that if Pu epsilon converges weakly in H10, then the zero extension is weakly convergent in theta u0. Because, okay, again, one write now here that u tilde epsilon, which is 0 in the holes and u epsilon outside, is equal to this product, because in the holes, key omega epsilon is 0 and u tilde epsilon is 0, so it's fine. And outside the holes, u epsilon tilde is equal to u epsilon. The extension operator is u epsilon, and the key holds 1. Okay, so we have this equality. And then if we pass to the limit as epsilon goes to 0, from the above convergences, we obtain that this one converges to u, this converges to u0, this converges to theta, this is strong weak. Then at the limit, u is equal to theta u0. Okay, now we want to show the convergence. So as before, as in computation, we have C epsilon equal A epsilon gradient to epsilon up to a subsequence is zero extension, which is bounded in L2, converges to some C0 in L2. Okay, so observe that we extended this one by 0. Then let V in H1 0, and we get that the integral of over omega xc tilde epsilon gradient of V, which is equal to that integral, and so to that one for the equation. And this one we can write like K omega epsilon FV integrating on the whole of omega. Then, at the limit, we have the integral, this one goes to xc0, here this one goes to theta, and the rest is fixed, so we have that equation, which means that minus divergence xc0 is equal to theta f. Okay. So now the question is, as before, what is the relation between xc0 and u0? And the answer is that xc0 is, like before, a0 gradient u0, but now the definition of u0 is different, is adapted to perforated domain, so a0 lambda is equal to the average over y of A gradient W lambda extended by 0, and W at lambda is lambda x minus K at lambda, where K at lambda is a solution of the same type of problem, periodic, that means periodic, Neumann on the holes, and of 0 average. I'm sorry, I didn't sleep this night. Okay, so the variational formulation is integral over y star a gradient K lambda gradient at gradient V equal a lambda gradient V for every V in H n pair. Then, okay, then due to the fact that divergence of xc0. So now we use this one, so we have that minus divergence of xc0 is equal to theta f, au0 equals 0 on the omega. Okay, hence the whole sequence converge, so that P epsilon, U epsilon converge to 0 weakly in H10 of omega. The 0 extension converges weakly to theta U0, and also Xc epsilon, which is this one, converges to Xc0 weakly in L2 by construction. And this quantity, which is called the momentum, is also an interesting physical quantity in the problem. Yeah, okay. Yes, because when actually the Neumann condition is coupled with the part in divergence form of the equation when you do some green integration. Now, since here you have this one, when you integrate by green, you get this term. And so, okay, you put all together, but... and then if you put, you call this one W at lambda, you have a minus divergence of W at lambda equals 0, and A gradient W at lambda equals dot n equals 0. But, okay, obviously it's not periodic, it's periodic plus affine. And the average of this W minus the affine is 0. No, okay, thanks for the question, because this was an interesting point, so it's clarified for everybody. Yes, so coming back to the result, U0 is the unique solution of this problem. Compared with the case without holes, we have A0 is different because the test solve a problem in the perforated cell. So the limit problem, remember, the perforation and the holes through A0, and also there is theta, which remember as the proportion of material. Some author now, this was the original way to write, now sometimes people put theta actually in A0. You can divide A0 by theta, then theta do not appear. So sometimes you will not find, you have to check that there are no error, but it's just a question of fixing A0. Okay, so as I remarked this morning, this is a normal Dirichlet problem which existence and uniqueness. So all the sequence we are involved, they converges, not only subsequence. So we have the P epsilon, U epsilon converging, tilde extension, and momentum. Voila. Okay. And then, what's that? Okay, there is a small error, small cut and copy. Actually, we have that, we define as above, transposed A0 lambda equal the average of the transposed of A gradient W lambda extended by 0. We take the key, and then we have the usual convergence. Okay, now, how we prove these results? Okay, we proceed exactly line by line as before, but there is some difference. There are some difference because now the integral are not on omega, but on omega epsilon, and the function are on the perforated domain, so we have to extend them. We cannot extend anything because we can extend the function because we have the extension operator, but for the gradient we can only extend by 0 as an L2 function, not by the extension operator. So we have just to pay attention when we extend. We have to extend because we need the convergences. So, okay, for the test function, we define again W epsilon lambda equal lambda dot minus epsilon. Okay, this is a tricky point. Okay, to have something, some test function which is still strongly converging to lambda x, the right way is to put the extension operator here and not here, because you don't know if the extension of lambda x is of the restriction of lambda x is still lambda x. Okay, so to avoid any mess, this is the right way. You take lambda, you define W lambda epsilon equal lambda dot x minus epsilon and the extension of the key lambda divided by, computed in x over epsilon. So in this case, since this is bounded, multiplied by epsilon goes to 0, so that W epsilon lambda strongly converges to lambda dot x. Moreover, W epsilon lambda is bounded in H1, so that W epsilon lambda weakly converges to lambda dot x also in H1. Then, as before, we introduce the flux related to the transposed. Now here we extend by 0, and once extended by 0, it converges to the transposed of A0 times lambda in L2, by definition, because it's like that. And also, as before, now the 0 extension of eta epsilon lambda verify the equation in omega. So now, again, Tartar, you choose phi in D, you choose the phi W epsilon lambda in the problem of U epsilon, and phi U epsilon in the problem of epsilon lambda. Again, the better term disappear, and you have these three terms. Now, what we do, we rewrite them by extension. So xi epsilon, which is only in L2, we extend by tilde. W epsilon lambda, it's already extended, so it's fine. Here, eta epsilon lambda we extend by tilde, and u epsilon by the extension operator p epsilon u epsilon. And here you just replace the integral over omega epsilon by the integral over omega, and you put inside the characteristic function of omega epsilon. Then you pass to the limit. Is easy because this go to xi0, this go to lambda x, this go to xi0, this go to u0, and so on. This go to theta w lambda x, and then you do exactly from now on the same computation as before, and you obtain then the desired result. Okay. Also, one have the convergence of the energy. That means that by similar argument as before, you can prove that the integral over omega epsilon, a epsilon gradient to epsilon gradient to epsilon, converges to the integral over omega is 0 gradient to 0 gradient to 0. Moreover, if we define the corrector matrix as before, except that here we put the gradient, the function defined in the perforated domain, then again we have the convergence gradient to epsilon minus c epsilon gradient to 0 in L1 going to 0, where here I pay attention that this integral is not in L1 of omega, but this is only in L1 of the perforated domain. Okay, there is no star, sorry, it's omega epsilon. Okay, so the proof is similar to the proof for a fixed domain using the equation and the extension operator, and I will skip it. I want to talk now about the homogeneous Robin boundary condition, which was more or less among the first, my first problem I studied in homogenization, first for very small holes, then for this case. It's very old results where we studied the non-homogeneous Robin condition. So we have here some epsilon to the power gamma, some rho epsilon of the form rho of x over epsilon, positive, periodic. Here we have g epsilon, which is the non-homogeneous condition. If we take rho equals 0, we get the Neumann condition. Otherwise, we have the complete Robin condition. Now, what about g epsilon? What we realized was that okay, the problem is linear, so you can put some epsilon or in the function or in the data is the same. So we prefer now write like that. So you say that if we put, if g, oh, sorry. Okay, so in this problem, what is very important is the g. The function g, which is here, is a periodic function coming from a function g which is defined on the reference hole t. So g, originally g is in L2 of t. Okay, now if the average of g is different from 0, we have to take epsilon g of x over epsilon in order to get bounded solution. Why? Because there is a boundary term which appears, and actually the total surface of the holes is not of order. Okay, let us discuss this point because it's important. Because I told you that the characteristic function of the holes go to theta. Why? Because go to something because it's bounded. Why is bounded? Because we have, if you have this situation, and this is epsilon, this is epsilon, how many holes you have? You have more or less 1 of order 1 of epsilon square here, in general 1 over epsilon to the power n holes. This is the number total of holes. Do you agree? Is the division of the square. Okay. Because here you have epsilon things of size epsilon. And so. Okay. So 1 over epsilon to the power n. Now, the total volume then is the number multiplied by the volume of 1. The volume of 1 is of order, is the measure of epsilon t, which is 1 over epsilon n. This is not exactly equal, is of order up to a constant, so this is of order 1 over epsilon n, epsilon to the power n, measure of t. Then this is of order of a constant, okay? Any question on that? Okay, now, but, if you compute now the total surface of the holes, okay, the number is the same, is the number of holes, so it's still 1 over epsilon to the power n. Now, what is, we have the measure of the epsilon t. Okay. And which is exact, something like 1 over epsilon to the power n. Then this is a consequence of Jacobian. I mean, this is a surface integral, so you have epsilon to the power n minus 1 times the measure n minus 1 dimensional of dt. So this is of order 1 over epsilon. Then imagine, okay, then the term, the boundary term, if you have a G with the not zero average, okay, you can show that it will be of order 1 over epsilon, and then you have to adjust that putting 1 epsilon. Or you compute, or you talk about epsilon, u epsilon, which is the same, epsilon, u epsilon divided by epsilon. So, finally, we choose, we have two cases. If the average is not 0, we choose epsilon g of x over epsilon here. If the average is 0, we can show that it's sufficient to put g of x over epsilon in order to have the result and the good a priori estimates. I will come back to this case average 0 because it seems because it actually is more difficult than the first case, except if g is 0. If g is 0, we are like before. Otherwise, it's more complicated. So let us look at the variational formulation. One can show that this is the variational formulation. The variational formulation is obtained formally as before. You multiply the equation by a regular function, then you make the integration by parts of the green formula, so that you replace the normal derivative by g epsilon minus epsilon gamma rho epsilon u epsilon, and then you have here this formulation, the usual term plus epsilon to the power gamma integral over dt epsilon rho epsilon v equal the term with f plus another boundary term g epsilon v. Okay, one can prove, which is not less obvious, but one can prove that you have existence, uniqueness by the Lax-Milgram theorem, using also the trace theorem because you have to estimate the integral of the boundary. Okay, Okay, so now you see that the situation is more complicated because not only we have integral of omega epsilon and we have to pass to integral of omega, but we have also the integral of the boundary. And there we cannot do so much because it's the integral on the boundary, which extension we can do of the integral of the boundary. So, okay, so let us see how we proceed. Okay, we can prove that the solutions are still bounded in V epsilon because we choose in a suitable way G epsilon. Then up to a subsequence P epsilon U epsilon converges to U0 in H10, and we want to know what is the limit problem. Here we assume that the boundary of T is of class C2 because we need some regularity results for PDEs. Actually, this is not necessary anymore in unfolding, but okay. So, which is the homogenization result? The homogenization result states that we have the same convergence as before, and here, what happens? We have V equals, the limit problem is still in omega, and we have two new terms. One, which is this constant, suppose that gamma is equal 1. If gamma is bigger than 1, this term do not exist. But if gamma is equal to 1, this term is the measure of dt over y multiplied by the average on dt of rho. And on the other side, we have the measure of dt over the measure of y multiplied by the average of dt over g. Okay. So what does it mean? Does it mean, it means that this integral, which was, the part with the u in, sorry, here I missed some u. You have to put u. This term correspond, let us look the equation, it's better. So this term on the boundary, this part of the condition becomes a zero-order term in the limit problem. And this data, which was only on the boundary of the holes, became a diffused data because it appeared in the right-hand side together with the F. That means that this is the equation. You have theta F as before, plus this term, which came from G, which is 0 if the average of G is 0, otherwise it exists, and here we have this other term. Okay. Just as a short sketch of the proof, okay, one use again the Tartar method, but we have to solve this problem about the boundary terms. So the idea is to use an auxiliary problem which was used for a different, completely in a different context for eigenvalue problems and their homogenization by Vanina Tan in a long time ago also, using I think he used this problem. I don't remember exactly. I think that he used this problem, but in a different way. So the idea is the following. You take the Neumann problem corresponding to the Laplacian in the perforated cell reference, and you put, let us fix some h. Then we use for different h. Then you have the Laplace problem equal to some constant. You have the Neumann condition equal h. You can show that actually CH has to be exactly this one because there is some compatibility condition. So this is the good CH that you can choose here, if you want H here, because if you integrate the Laplacian, you have just the integral of this one, which will be the integral of this one, so you have this condition. Then, if you extend this solution to the wool over N perforated by periodicity, what is the equation? The equation is epsilon times the gradient on the boundary of the holes, h x of epsilon v equal to this product plus ch integral over omega epsilon v dx. Okay, so now one prove that actually this term is of order epsilon, so it goes to 0, and this term converges so to the limit of this term, which is nothing else than ch multiplied by theta integral of v. So that means that we can state the following things. Let me epsilon h, the function which to any v in h10 of omega, associate epsilon integral over dt epsilon of h of x over epsilon multiplied by v. Then this function belongs to the dual, that means it's linear continuous, and it strongly converges in the dual to the mu h, where mu h is just the function that to any v associate the theta ch integral over omega v. Sorry, here there is no h inside. Okay, so the case where the mean value of g is different from 0 is solved. Now, the situation is more difficult for the case where the average is 0, because we can prove that we have the a priori estimates, so we cannot multiply by epsilon, otherwise we have nothing at 0 everywhere. But now the related measure here, because we have not epsilon, we have only weak convergence and not stronger convergence. And this is a problem because it will be multiplied by things which are also weak. We have weak, and we cannot pass to the limit. So we did some tricky argument in order to solve using some auxiliary problem in order to show the convergence. Okay, now all that can be also done by unfolding, as I told before, and then, okay, one can cover those results. Okay, now a last 2 slides, which are quite interesting, concern the convergence of the energy at the correctors. Where the results are really different for the case of 0 average and the case of non-zero average. In the case where we have epsilon g of x over epsilon with non-zero average, where we have the strong convergence of the measure and so on, okay, the result is easy. One gets the usual convergence of the energy and the usual result of corrector. So, okay, everything is fine. Now, the case where the average is 0, but g is not identically 0, obviously. Okay, actually, at that moment, we were not able to do it for a long time. We were not able to study the corrector of that problem. More or less, Doina Sharanescu have some asymptotic expansion, but it was not so clear. And actually, we proved the corrector result only a few time ago with my former PhD student, Imen Shurabi, in 2015 only, so more 25 years after actually the other results, using the periodic unfolding method, which show once more that this method has some advantage, because this is the first results I know that was not possible to do before, at least in my results. Maybe there are other results, but okay. That one I was not able to do without so the result is the following, which is a bit surprising, because you have this convergence in L1, gradient u epsilon minus c epsilon gradient u 0 minus the gradient in y of the periodized function of this key at g. So before the key at G, we have no key at G. Now, there is this term, this gradient, which has to be subtracted in this formula. And who is key at G? Key at G is the solution of the problem minus A gradient key at G equals 0 in the perforated hole, A gradient at G dot V equals G. This is good because also the average of G is 0, so the compatibility condition is satisfied. Key at G is wide periodic and the average is 0. Okay, so this is, I think, my last slide. No, not at all. I have another, I forgot, sorry. I have 10 minutes more, so. Okay, now I want to talk, sorry, about a completely different framework, which, what we have done till now, we take a cell, we did the hole, we did an homotopy global of the perforated domain, so we had a small cell of size epsilon y, a small hole of size epsilon t. What we want to do now is to reduce y to the size epsilon, but to reduce the hole a lot more, to a smaller size. And this is what was done in the original paper of Ceranescu-Murat in 82. And there is an interesting phenomenon, they call it the strange term phenomenon. In French, it was a strange term coming from elsewhere, something like that. Coming from nowhere, yes, thank you. Who told that? Ah, Daniel. Okay, I'm a little bit sleepy, sorry, because this night I wake up very early. Okay, so not like you, I know, he was, but you are used to don't sleep too much, maybe less than me. I am a sleeper. Okay, since then, thank you. Since then, there are an incredible literature where in a lot of situations there are studied many problems in this kind of domain, and anytime you have some strange term phenomenon. Okay, what is this phenomenon? Okay, so they wrote the paper in a very abstract and general situation. I will describe the simple case where the all are bolts, and so we take a connected domain, we take for simplicity n bigger or equal than 3. The case n equal 2 is also solved, but more complicated for the size. Then what we do? We choose, for simplicity, y equal minus 1, 1. So we have our this is minus 1, 1. And here we have the ball of size 1. No, there is something wrong. Doesn't matter. No, it's okay. We have the ball of size 1. But now we string more the holes than y. And so what we do? We take a sequence of epsilon which tend to 0. We take a epsilon smaller than epsilon for any epsilon, and even of order smaller than epsilon, in the sense that the limit of a epsilon over epsilon goes to 0. Then we take the set of the holes, any holes as of the form a epsilon b1 plus ky. That means that we have the repeated holes, but the size of holes is a epsilon, and the size of the here epsilon is missed too, sorry. So this is now, the situation is that the holes is a epsilon t, and this one is epsilon y as before. I forgot one epsilon. Okay, so we define the perforated domain. like omega minus T epsilon. So we have also of size A epsilon smaller than the period 2 epsilon. And then the homogenization result is the following. We consider the Dirichlet problem everywhere, again, and we have delta here. So if for some constant C0, A epsilon is of order epsilon to the power n over n minus 2, which for in three-dimensional means epsilon cube, then we have that the zero extension of the epsilon converges weakly to some u, is gradient, which is his energy, converges to this energy. Okay, the mu is just simply mu dx, so here, where u is the unique solution of minus delta u plus mu u plus equal f. Okay, this is omega, sorry, also. Okay, that means that there is this term, zero order term, which is the strange term, coming, nobody knew at that moment. It seems like coming from nowhere exactly, but actually there are some reason of this term that one can understand, so that we have this zero order term. Moreover, the constant mu is this constant multiplied by the capacity of the ball of radius 1 times Rn, where this capacity is the infimum of the L2 norm in Rn of the function, which are 1 of the ball and in D of Rn, which is more or less the solution of the problem, which all is 1 in the ball, 0 outside, and harmonic. Okay, and so this quantity is called the capacity in Rn of a closed of the set B1. Capacity is an important notion. People in probability use a lot because it has an important signification, and has been widely studied, is very interesting, but I don't want to discuss here that one. I want just to do some important remark. The first one is that this size was called the critical size because something special happens. If the size is bigger, actually the limit of the solution is 0, so it looks like the case epsilon. If the size is smaller, then nothing happens. We have no strange term, we have just the expected problem, here no epsilon. Okay, the case now, another remark is that actually this case of A epsilon was not studied originally, but it was not one, not by hazard, because they were not able to do that, because the test function they use are not adapted to have oscillating coefficient. And if you use the test for oscillating coefficients, it's not adapted for the small holes. Okay, so long time after, there was a Russian, I forgot the name, probably Skripnik, but I'm not sure, who proved the result for this case long time after. And then Dalmaso Murat did the proof, but in a very complicated case, nonlinear, with the p instead of 2. And so all that was very complicated. Okay, now, by unfolding, Doina, Joronesco, Lendam, Lamian, Grisot, and Daniel proved the result for this case with using the periodic unfolding method. So the proof is not is a lot more simple than the previous proof in this case, and one can use the oscillating coefficients. Okay, so final remark is that in the abstract case, mu is not a constant but is a measure. In this case, you can have also different form of holes, which is important is their size. Okay, so now I really stop here. Thank you.